This is SpaceTime Series 29, Episode 79, for broadcast on the 3rd of July 2026. Coming up on SpaceTime, how neutron stars make heavy elements, the Aleutian subduction zone looks like it's older than we thought, and the wobbling peanut asteroid. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Physicists have achieved a significant breakthrough in understanding how neutron stars forge heavy elements. The findings, reported in the Astrophysical Journal, show that a perceived roadblock preventing the formation of high-mass elements is far weaker than previously thought. Stars shine by fusing hydrogen into helium in their cores through a process called nucleosynthesis. When they run out of core hydrogen, they begin fusing helium into oxygen and carbon. Now, for low-mass stars like our Sun, that's pretty well where the process ends, and the stellar remains then turn into a stellar corpse called a white dwarf, surrounded by an ever-expanding planetary nebula. But for higher-mass stars, this nucleosynthesis can continue, producing increasingly heavier and heavier elements until ultimately iron is produced in the stellar core. Now, no matter how big a star is, how much mass it has, no star is large enough to fuse iron into heavier elements. And so the process ends, and gravity takes over, crushing the entire mass of the star down into its core, which then rebounds, exploding outwards in what's called a core collapse supernova. This blast produces many of the elements heavier than iron on the periodic table, and it leaves behind a stellar core called a neutron star. These are the densest objects in the universe other than black holes. In fact, just a teaspoon of neutron star material would weigh billions of tons. So, an object with more than 8 times the mass of the Sun can be crammed down into a ball just 12 or so kilometres wide. But the story doesn't end there. The heaviest elements in the universe are generated when 2 neutron stars in a binary system merge in what's called a kilonova explosion. This violent event triggers a rapid neutron capture process, which creates elements like gold, platinum, silver, uranium, thorium, and iodine. But it doesn't have to be 2 neutron stars. In some binary systems, neutron stars pull material off conventional stars, creating extreme temperatures and pressures which trigger powerful bursts of X-rays. Recreating these sorts of processes in the lab would help explain many unanswered questions about the universe and how it works. The study's lead author, Jasprit Radawar from Mississippi State University, says by identifying how stellar explosions build heavier elements, scientists can gain a clearer picture of how the elements that form planets and support life are distributed through the cosmos. Radawar and colleagues wanted to know whether nature had a built-in roadblock that stopped heavier elements from forming during X-ray bursts on neutron star surfaces. But the authors showed that this roadblock is much weaker than expected, meaning the processes that build heavier elements can continue. Scientists long suspected that the processes forming heavier elements in these bursts could stall at the element copper-59, a short-lived isotope that decays in less than 2 minutes. Radawar says that brief window has made it difficult for researchers to study the reaction in the laboratory, and that's posed a major challenge for direct measurements. In this new study, Radawar and colleagues produced a beam of copper-59, accelerated it, and then directed it onto a frozen hydrogen target before it decayed. The experiment at Canada's National Laboratory for Nuclear and Particle Physics was the first direct laboratory measurements for this key reaction, and it helped solidify our understanding of how the universe works. This is SpaceTime. Still to come, the Aleutian subduction zone found to be much older than previously thought, and the wobbling peanut asteroid Donald Johanson. All that and more still to come on SpaceTime. A new study has found that the subduction zone between the Pacific and North American tectonic plates is far older than previously thought. The findings, reported in the journal Nature Communications, are based on rock samples collected from key parts of the Aleutian Arc Island chain. The authors determined the age of the rocks using 2 independent dating methods: uranium-lead dating from zircon crystals and argon-argon dating of volcanic rocks and minerals. They found the oldest traces of subduction are at least 56 million years old, showing that the process began much earlier than many previous models had suggested. This earlier age is important because it places the birth of the Aleutian subduction zone at the start of a major chain of tectonic events and a reorganization of plate motions right across the Pacific. During this interval, several subduction zones and volcanic arcs around the Pacific were formed. A spreading centre mid-ocean ridge was subducted, and a large igneous province collided with the North American margin. The Aleutian arc, therefore, appears to represent one piece of a much larger tectonic puzzle. This is SpaceTime. Still to come, the wobbling peanut asteroid, and planet Earth at its greatest distance from the Sun, the constellations Regulus and Leo, and one of the biggest known stars in the universe, Antares, are among the highlights of July's night skies on Skywatch. Okay, let's take a break from our show for a word from our sponsor, Incogni. If you're anything like me, you're probably concerned about your privacy online. And for good reason. Did you know there are hundreds of data brokers out there quietly collecting, buying and selling your personal information? Now, I'm talking about your phone number, your home address, your browsing habits, even your location history. And that's where Incogni comes in. Incogni is a service that acts on your behalf, requesting the removal of your personal data from these shady data brokers. And they don't just send a one-off email. They follow up, track responses, and ensure that your data actually does get deleted. Think of it as having a digital privacy agency constantly working for you behind the scenes. And the best part, it's all incredibly easy. You just sign up, give them the go-ahead, and Incogni take care of all the rest. And within just a few weeks, you'll start seeing the results. There'll be fewer spam calls, less targeted advertising, and a genuine sense of relief knowing that your private data is no longer being traded like a commodity. Now, as a SpaceTime listener, we're offering you a special discount deal. Just go to incogni.com/Stuart Gary. That's incogni.com/Stuart Gary. And if you're not completely satisfied, no worries. Incogni offers a 30-day money-back guarantee, so you can try it out risk-free. You know, protecting your privacy really shouldn't be optional in this digital age. So let Incogni help you by keeping your personal information where it belongs, with you. That's incogni.com/Stuart Gary to access this exclusive discount offer and learn more. Stay safe, stay private with Incogni. Astronomers studying the inner main dot asteroid Donald Johanson have found that its rotation wobbles. Rather than rolling through space in a steady pattern, Donald Johanson turns on two separate axes, rotating end over end once every 10.5 Earth days, while wobbling around its horizontal axis every 26.5 Earth days. The study's lead author Simone Marchi from the Southwest Research Institute says it's just one of the many surprising things learned by NASA's Lucy spacecraft as it flew by Donald Johanson back on April the 20th, 2025. Marchi, who's deputy principal investigator on the Lucy mission, says Lucy's images confirm the asteroid's elongated shape, which was initially suggested through Earth-based telescope observations. The Lucy flyby revealed that this small kilometre-sized asteroid really does resemble a peanut, with a two-lobed structure connected by a narrower neck. Lucy also detected rich iron clay minerals formed long ago from the presence of liquid water. Now, these findings could indicate the asteroid formed from fragments of a larger carbon and water-rich asteroid, which would have broken apart some 155 million years ago, following a collision with another object in the main asteroid belt, a region between Mars and Jupiter. Lucy's encounter with Donald Johanson was considered a test run for its primary mission to explore the Trojan asteroids, two swarms of ancient objects that lead and trail Jupiter as the Jovian giant orbits around the Sun. Astronomers think these two populations of space rocks have been preserved since they formed in the early history of our solar system. Marchi says once we start learning more about the Trojans, a completely different population of space rocks with very different histories, science's understanding of our solar system's formation is likely to be changed forever. By the way, the asteroid Donald Johanson, well, it's named after the paleontologist Donald Johanson, who discovered the famous Lucy fossil, an early Australopithecus hominid found in Ethiopia back in 1974. Lucy was one of the oldest human ancestors ever found, and was the inspiration for the Lucy mission's name. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for July on Skywatch. July is the 7th month of the year in both the Julian and Gregorian calendars, and is named after the Roman Emperor Julius Caesar, who was born during the month. Before being called July, the month was called Quintilis, which is Latin for fifth. The addition of the months January and February brought an end to that. On average, July is the coldest month in the year in the southern hemisphere, which is experiencing winter, and also marks the time when Earth is at aphelion, its furthest orbital position from the Sun. Of course, temperatures, or more accurately seasons on Earth, aren't dictated by the distance from the Sun, but rather the length of a day, and hence the amount of sunlight a given part of the Earth receives, which is governed by the tilt of Earth's axis. Consequently, that's why July is on average the warmest month in the Northern Hemisphere, which is currently experiencing summer. Aphelion will happen at 3:30 in the morning of July the 7th, Australian Eastern Standard Time. That's 1:30 in the afternoon of July the 6th, US Eastern Daylight Time, and 17:30 in the afternoon, Greenwich Mean Time. During this year's aphelion, Earth will be 152,087,775 kilometres away from the Sun. That's about 5 million kilometres further away than during perihelion back in January. Over cosmic time, these dates change. That's due to variations in Earth's orbit, such as eccentricity, as well as axial tilt and precession, which all follow regular cyclic patterns known as Milankovitch cycles. Eccentricity involves changes in how elliptical Earth's orbit is around the Sun. None of the planets actually orbit the Sun in perfect circles, although Venus and Neptune are the closest. Instead, they all have elongated orbits which vary over time. As well as that, Earth spins on an axis which is currently tilted at 23.4 degrees compared to the ecliptic, Earth's orbital plane around the Sun. But this angle of tilt also changes over time, influenced by, among other things, the distribution of the Earth's mass. And just like a spinning top, the rotational axis of the Earth also changes its orientation through a process called precession, changing its position in relation to fixed background stars over a 26,000-year cycle. Now, all these effects impact the amount of solar radiation reaching the Earth, what time it reaches the Earth, and consequently the planet's seasonal and climatic patterns. Right now, the Southern Cross is at its highest point in the southern sky, and is pointing directly towards the southern celestial pole. The Southern Cross falls within the constellation Centaurus the Centaur, the half-human, half-horse of Greek mythology, and the creature is holding a bow loaded with an arrow. The Centaur's front legs are marked by the two pointer stars, Alpha and Beta Centaurus. At 4.3 light-years, Alpha Centauri is the second of the two pointer stars from the Southern Cross and is also the nearest star system to the Sun. The Centaur's back arches over the Southern Cross, and just above this is Omega Centauri, a spectacular globular cluster, visible with the unaided eye from dark locations. Globular clusters are tightly packed spheres containing thousands to millions of stars. They're thought to have all originally been born at the same time from the same molecular gas and dust cloud, or they're the cause of small galaxies which have been consumed by bigger galaxies through galactic cannibalism. Omega Centauri is about 16,000 light-years away. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Omega Centauri is one of the largest and brightest of the 150 or so globular clusters known to orbit around our Milky Way galaxy. Centaurus was one of the 48 constellations listed by the 2nd century astronomer Ptolemy, and it remains one of the 88 modern-day constellations. Turning to the right or west, and you'll see the constellation Leo the Lion, just above the western horizon. Its brightest star is Regulus, or the Little King, located about 79 light-years away. Regulus, designated Alpha Leonis, is actually a 5-star system, organised into 2 pairs. Regulus A is a spectroscopic binary, comprising a spectral type B blue-white main sequence star, some 4 times the mass and 288 times the luminosity of the Sun, and a faint companion star thought to be a white dwarf, the stellar corpse of a Sun-like star. Spectroscopic binaries are stars that can't be resolved by optical telescopes into 2 separate objects, and can only be separated by observing their individual spectroscopic Doppler shifts as they orbit each other. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive known stars are spectral type M red dwarf stars. Each spectral classification is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. So put all that together, and our Sun is a spectral type G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red dwarf stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which can be about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which can be 75 to 80 times the mass of Jupiter, or 0.08 solar masses. Located further away are Regulus B, C and D, which are dim main sequence stars. At the opposite end of the constellation from Regulus is the star Beta Leonis, or Denebola, the horse's tail. It's also a luminous blue-white star, about half as bright as Regulus, and the third brightest star in the constellation Leo. Beta Leonis has about 1.8 times the Sun's mass and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Delta Scuti type variable star, meaning its luminosity varies slightly over a period of several hours due to pulsations on its surface. Algebra or Gamma Leonis is a binary system with a visible third component. The two primary stars are located about 126 light-years away and can be resolved in small backyard telescopes. Both are yellow giants orbiting each other every 600 Earth days. The unrelated tertiary star named 40 Leonis is a yellow tinge star that can be seen through binoculars. The star's traditional name Algebra means forehead. Delta Leonis or Zosma is a blue-white star 58 light-years from Earth. Epsilon Leonis is a yellow giant some 251 light-years from Earth. And Zeta Leonis is an optical triple star. The brightest component is a white giant about 260 light-years from Earth, while the second brightest star, 39 Leonis, is widely spaced and located to the south of the primary. The third and faintest star in the system, 35 Leonis, is to the north. Lota Leonis is a binary star system visible in medium-sized backyard telescopes. Located some 79 light-years away, Lota Leonis appears to be a yellow tin star with two components orbiting each other every 183 Earth-years. Finally in Leo, let's look at Tau Leonis. Visible as a double star through binoculars, it includes a yellow giant located some 621 light-years from Earth, and binary secondary star 54 Leonis, which is actually a pair of blue-white stars that are visible in small telescopes and located some 289 light-years away. The constellation Leo also contains many galaxies, including the spiral galaxy Messier 66, as well as Messier 65 and NGC 3628, which are known as the Leo triplet. Located some 37 million light-years away, the Leo triplet has a somewhat distorted shape due to gravitational interactions between Messier 66 and the other two galaxies, which are cannibalizing stars from Messier 66. Eventually, the outermost stars may well form a dwarf galaxy orbiting M66. Both M65 and M66 are visible in large binoculars or small backyard telescopes, but their concentrated nuclei and elongation are only visible in larger instruments. Other bright, well-known deep sky galaxies in Leo include Messier 95, Messier 96, and Messier 105. Messier 95 and Messier 96 are both spiral galaxies, each about 20 million light-years from Earth. Both look like fuzzy objects in small telescopes, but display their spectacular structures in larger instruments. M95 is a barred spiral. Another barred spiral, NGC 2903, is thought to be similar in size and structure to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also about 20 million light-years away. The constellation also contains the Leo Ring, a cloud of hydrogen and helium gas orbiting two of the galaxies in the constellation. A gravitationally lensed object known as the cosmic horseshoe is also found in Leo. Above Leo, you'll find the constellation Virgo, the Greek and Roman goddess of wheat and agriculture. Virgo's brightest star, Spica, is visible above the western horizon. It's located some 250 light-years away. Spica is Latin for ear of wheat, which Virgo is holding in a hand. Spica, or Alpha Virginis, is the 16th brightest star in the night sky, and is both a spectroscopic binary and a rotating ellipsoidal variable, a close binary system whose stars are not eclipsing but cause apparent fluctuations in brightness because of changes in the amount of light emitting area visible to the observer. Spica's two main stars orbit each other once every 4 Earth days and are so close they're egg-shaped rather than spherical and can only be separated by their spectra. The primary is the blue giant variable Beta Cepheid star. It undergoes small rapid variations in brightness. These are caused by pulsations of the star's surface, thought to be caused by the unusual properties of iron at temperatures of 200,000 degrees in the stellar interior. It has about 10 times the Sun's mass and about 7 times its diameter. The secondary star in Spica is smaller than the primary, but it's still some 7 times more massive than the Sun and has 3.6 times the Sun's diameter. Turning to the north now, and the constellation Boötes, the herdsman or ploughman. There you'll see the bright orange-red star Arcturus, or Alpha Boötes, just above the northern horizon. It's a red giant located just 36 light-years away, a bloated, aging star some 7.1 billion years old, nearing the end of its life. Although not much more massive than the Sun, it's now expanded out to some 25 times the Sun's diameter and will soon puff off its outer gaseous envelope as a planetary nebula, revealing its white-hot stellar core, a white dwarf, which will then slowly cool over the eons of time. Another bright reddish-looking star, this time in the east, is the red supergiant Antares, meaning the rival of Mars, because of its appearance and location in the sky, which appears to be opposite of Mars in the sky. Antares is one of the biggest known stars in the universe. It's enormous, 18 times the Sun's mass, 10,000 times its luminosity, and 883 times the Sun's radius. As we mentioned in last month's Skywatch, were it placed at the centre of our solar system, its surface would extend out close to the orbit of Jupiter. Despite being some 550 light-years away, Antares is still the 15th brightest star in the night sky. Unlike the Sun or Arcturus, the death of Antares will be far more spectacular. Antares is destined to explode as a core collapse or Type II supernova. When it does so, sometime in the next few 100,000 years, it'll appear as bright in the Earth's sky as the full moon and be quite visible even in daytime. Antares has a companion star, Antares B, a spectral type blue-white main sequence star more than 7 times the Sun's mass and 5 times its diameter. Antares is the heart of the Scorpion in the constellation Scorpius. Below Scorpius is the constellation Sagittarius, the Archer, which points the way to the centre of the Milky Way galaxy. Sagittarius is commonly represented as a winged centaur. The centre of the Milky Way galaxy and its supermassive black hole Sagittarius A star lie at the westernmost part of Sagittarius. Sagittarius A star is about 27,000 light-years away and has some 4.3 million times the mass of our Sun. It was in July back in 2016 that the solar system's barycenter moved outside the Sun, where it will remain until 2027. A barycenter is the gravitational center of mass of a celestial system. For example, in our Earth-Moon system, the Earth and Moon actually orbit each other around a common center of gravity, a barycenter. Now, because the Earth is so much more massive than the Moon, the barycenter is always inside the Earth's radius. If it were outside the Earth's radius, the Earth and Moon would instead have been classified as a binary planetary system, like Pluto and Charon. The solar system's centre of gravity or barycenter is usually located inside the Sun's radius. After all, the Sun contains over 99% of all the solar system's mass. But actually, the mass of the solar system is orbiting around the solar system's barycenter, which means the Sun also has a very slight spiraling 12-year orbit around the barycenter. And every now and then, when the planet's orbital positions are just right, especially when Jupiter and Saturn are nearest each other, their combined gravitational interactions move the solar system's barycenter ever so slightly outside the Sun's radius. And because Jupiter and Saturn reach this alignment every 11 years, some scientists have speculated whether this could trigger the Sun's 11-year solar cycle. And before you ask, the barycenter isn't named after some guy in a beige safari suit called Barry, but rather it's the ancient Greek word for heavy or center of mass. We also have 2 meteor showers, both of which peak in late July. There's the southern Delta Aquarids, which are visible from mid-July to mid-August each year, with peak activity on July the 28th and 29th. The shower originated either from the breakup of what are now the Marsden and Crack sun-grazing comets, or from the parent comet P96 Malkolts. The Delta Aquarids get their name because their radiant appears to lie in the constellation Aquarius, near one of the constellation's brightest stars, Delta Aquarii. There are 2 branches to the Delta Aquarids meteor shower, the southern and northern. The southern Delta Aquarids are considered a strong shower, with an average of between 15 and 20 meteors an hour between midnight and dawn. Listeners in the southern hemisphere usually get the better show because the radiant is higher in the southern sky. Since the radiant is above the southern horizon for northern hemisphere listeners, meteors will be seen to fan out in all directions east, north and west, with few meteors heading southwards, unless they're really short near the radiant. The northern Delta Aquarids are the weaker shower, peaking later in mid-August, with an average peak rate of about 10 meteors per hour. Meanwhile, the nearby slow and bright Alpha Capricornids meteor shower will take place from as early as July the 15th and continue until around August the 10th. The meteor shower has infrequent but relatively bright meteors and even some fireballs. It's generated as the Earth passes through a debris trail left by the comet 169P Neat, which was originally identified as the asteroid 2002 EX12. However, it was shown to be weakly active during perihelion and was then reclassified as a comet. The meteor shower was created about 3,500 to 5,000 years ago, when about half of the parent body disintegrated and fell into dust. The cloud eventually evolved into Earth's orbit, causing a shower with peak rates of about 5 meteors an hour and some outbursts of bright flaring comets, radiating out from the constellation Capricorn towards the south. The bulk of the comet's debris won't be in Earth's path until the 24th century, by which time the Alpha Capricornids are expected to become a major annual meteor storm, stronger than any current annual shower. And joining us now for the rest of our tour of the July night skies is senior science writer and Sky and Telescope magazine contributor Jonathan Nally.
G'day, Stuart. Yeah, well, it's July, and amateur astronomers actually love this time of year for stargazing because those who live in the northern half of the planet have the advantage of it being summer at the moment, so the weather's usually pretty nice and warm and quite pleasant, although it does mean, of course, that summertime means you have fewer hours of darkness because the daytime's longer, but, your nighttime weather is generally a bit nicer for going out and stargazing. So that's pretty good, and those of us who live in the southern hemisphere, we love July as well, even though it's colder, but the nights are longer, and particularly down here we have an advantage of the fact that the centre of our Milky Way, our galaxy, Milky Way is our galaxy seen from the inside, and when we look in a particular direction, we're looking into the centre, the core of our Milky Way, and that means there's lots of things to see there. And that region is the region in and around Sagittarius, the constellation Sagittarius, and also the neighbouring constellation Scorpius. Scorpius is not directly in line with the centre of the galaxy, but there's still a lot of great stuff to see there. This area in the sky is full of amazing astronomical objects, all the usual things that amateur astronomers like to see, of star clusters of both kinds. You've got globular star clusters and open star clusters, and there are nebulae, both bright ones and dark ones. There are lots and lots of interesting star patterns. Nebulae, for instance, Sagittarius has the famous Lagoon Nebula, which is really, really pretty, and there's the equally famous Trifid Nebula. People might have seen pictures of the Trifid Nebula. It's a reasonably hard one to spot. The really hard one to spot in the night sky is in Orion, which can't be seen at the moment, and it's called the Horsehead Nebula. And when you look at pictures of it, you think it's really really fabulous and looks really big and everything, but it's actually tiny in the sky and it's very, very hard to spot. But the Trifid Nebula, Lagoon Nebula up in Sagittarius, really, really good. Down in the southern part of the sky, at least for us here in the southern hemisphere, we've got the Southern Cross. It's up nice and high, standing almost upright with a pair of bright stars nearby. We talk about these a lot on the program. They're called the pointers because if you draw a line between the pointers and keep the line going, it heads basically straight towards the Southern Cross. So it's an easy way to find the Southern Cross. One of those pointer stars is the star system called Alpha Centauri, which is the closest system to ours, which has two bright stars that are quite like our sun, and they're fairly close together, and there's a third very, very dim star that's further away. That one is actually the closest star to our solar system. It's very hard to see that one unless you know exactly where you're looking for and you've got a big telescope. So to the unaided eye, Alpha Centauri, the Alpha Centauri system looks like just a single star, but even a small telescope, you can just get a small refractor, a small telescope, cheap one, that'll split those two main stars. You see them as separate entities. So that's pretty neat. You look up and think, oh, that's one star. And when you have to take a closer look, it's two stars, and there are plenty of examples of those up in the night sky. So over to the right of the Southern Cross, also within the Milky Way, is a fantastic area to see. Right next to the cross, for example, there's a large dark patch in the Milky Way. Now, this is pretty hard to see under city skies because you've got not much hope of seeing the Milky Way at all, I'm afraid, under city skies. But if you do get an opportunity to get out somewhere dark, away from light, and you let your eyes get dark adapted and you can see the Milky Way, well, have a look just to the side of the Southern Cross and you'll see this dark patch. And it's called the coal sack for obvious reasons because it's black. And it's just a big cloud of interstellar gas and dust that is out there in our galaxy. It's interesting, you go back to, not too long ago really in terms of history, 150 years or so, or maybe a bit less. People really didn't know whether that was a big hole in our galaxy and we were looking straight through out to the other side, or could it be, yes, a big dark cloud or something. And so it turns out to be a big dark cloud because even to the naked eye, you can see a few stars in there. So when you get telescopes under it, you can see there are stars in front of it and behind it and everything. So it's a big cloud of dark gas and dust. Now, the northern half of the sky, for this time of year, at least for where I am when I'm looking to the north, looks pretty bare. But there are a couple of bright stars. We've got one called Spica, which is the brightest star in the constellation Virgo. There's another one called Arcturus, which is the brightest star in the constellation Boötes. That's not a constellation most people are familiar with. It's spelled Bootes, and it means the herdsman or the ploughman. Arcturus is actually the fourth brightest star in the night sky, and Spica is the 16th brightest star. So they're pretty bright as stars go. And spanning all across the northern half of the sky, as seen from down here in the south, we've got the zodiac region, the zodiacal region. So Virgo is one of those zodiacal constellations. It's a very large star pattern, Virgo, and it seems quite bare to the naked eye, but to amateur astronomers, they love it because once you get a telescope in there and start looking around that region, there are stacks of galaxies, including that big one, M87. That's the one that has the big black hole in the middle of it. And they've made that famous picture a few years ago of the black hole.
The first ever direct observation of a black hole.
I think it was called the Event Horizon Telescope, or a combination of telescopes. Yeah, and they made people will say, well, how can you see a black hole if no light is getting out of it? Well, really, you're seeing what's around the black hole, and there's a gap in the middle. So that was the black hole. So that was pretty amazing. There's another really fantastic galaxy in Virgo too. Now, this one also is really small. You see pictures of it, you think, well, it's a galaxy, it's got to be big. But when you go hunting for it with a telescope, it's really small. It's called the Sombrero Galaxy because it's this almost side-on spiral galaxy with a dust flame running through its middle.
Beautiful looking galaxy.
Oh, it's a wonderful galaxy. It's really superb. And it looks like a sombrero. It looks like a hat slightly tilted towards us.
You can see the dust lanes and areas of starbirth. It is stunning.
It's a fantastic thing. But as I say, the pictures taken with big telescopes look really impressive. But through a backyard telescope, it's actually quite small, very small, in fact. And you need to take a good long look to get any detail at all because these things, A, are small and B, they're dim. And our eyes are not good at night time compared to daytime, which is why things look so much better in pictures when you're taking pictures of the night sky, because cameras can do a lot better than our eyes do. Anyhow, that's what's happening with all the constellations and things. Let's look at the planets now. So there's quite a bit going on above the northwestern horizon at the moment as July opens. We've got Mercury, Jupiter and Venus in that order going upwards from the horizon, and they can all be seen quite easily. Mercury is very low, I have to say, and it looks a bit like a small, intense dot of light. Jupiter and Venus above it are much bigger and much brighter. Mercury, though, is soon to disappear by about the 8th or 9th of the month. It will have dropped below the horizon. It's getting lower each night. So it's going to fade into the sunset glow and then be below the horizon. Jupiter, too, is doing the same thing. It's getting lower and lower down on the horizon as each night goes past it this month. And by about the middle of the month, 16th, 17th or so, it'll be down below the horizon. Venus, on the other hand, is climbing higher and higher each day during July. So you'll have plenty of opportunities to see it. You can't miss it. Big and bright. It's the biggest, brightest thing around in that part of the sky, apart from when the moon is nearby. So if you want to have a look at Venus, get out now this month and do it. It's a really good time because it's going to be up nice and high. It'll be around for several hours after sunset, so that's a pretty good time to see it. The other two bright planets that we can normally see are Saturn and Mars. These are a bit later in the night. Saturn will pop its head over the eastern horizon just after midnight at the beginning of the month, but earlier by the end of July, about 10:30 p.m. So it's getting higher and higher, that means, as the days go past. And about 4 hours behind Saturn, only probably hour and a half, 2 hours before dawn, I suppose, we've got Mars. That'll follow up over the eastern horizon as well. A bit more to the northeast. Saturn's pretty much directly east. Mars will be a bit more to the northeast, and it's much smaller and dimmer than Saturn. Saturn looks big and bright and maybe with a slightly yellowish, orangish sort of tinge or yellowish tinge. Mars is smaller and has a definite orangey red sort of colour. And that's one of the ways you can often tell Mars, because there aren't that many bright stars up there that are that kind of colour. So Mars is pretty easy to spot. And if you are up early to take a look at Mars at the beginning of the month, like in the first few days of the month, you're in for an added treat, in fact, because only about 5 degrees away will be the famous star cluster known as the Pleiades, or the Seven Sisters. This is this fantastic little clutch of stars. Most people can see 6, maybe 7, but usually 6 of these little stars. There are hundreds and hundreds and hundreds of stars in this cluster, but they're too dim for the unaided eye. So yeah, Mars will be about 5 degrees away. 5 degrees is about 10 widths of the moon. The moon's about half a degree wide, so that's pretty close. You certainly should get a good view of that. But as I say, you've got to be up pretty early, a couple of hours before dawn, or if you're a night owl, if you know anyone like that, Stuart, who stays up all night and
you're talking.
Looks the night sky.
Yeah, you're talking to him.
Yeah. Well, we want to report next month. We want to report on how Mars looked with the Pleiades right next.
Oh, look, I'm still getting over last month's spectacular conjunction between Jupiter and Venus.
I was going to ask you about that. How did you go?
That was beautiful, absolutely stunning. And speaking of the Pleiades, which you were a moment ago, the latest speculation is that a supernova in the Pleiades may have been what caused the birth of our own sun. At least that's the latest speculation.
Well, by compressing gas and getting a chain reaction going to hold a big cloud of gas.
Because they're all very young stars in the Pleiades.
I wish I was a young star again, but now I'm collapsing like our sun. And that, Stuart, is the sky for July.
That's senior science writer and Sky and Telescope magazine contributor Jonathan Nally, and this is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.